In Yellowstone National Park, geologists say one of the park's famous geyser basins now has a new hot spring.
Satellites orbiting high above the Earth recently captured subtle but alarming changes in the surface of Yellowstone National Park, prompting geologists to issue a rare and urgent red alert. The warning, focused on the supervolcano that lies beneath one of America's most iconic natural landscapes, has ignited serious concern among scientists monitoring the region. This supervolcano, known for its potential to unleash one of the most cataclysmic eruptions in human history, appears to be undergoing significant subsurface activity, and the implications are far-reaching. Before we start, smash the like and subscribe buttons for more updates. Yellowstone's massive volcanic system, centered within the park that spans parts of Wyoming, Montana, and Idaho, has long been the subject of intense scientific observation. Beneath its seemingly tranquil geysers, hot springs, and rugged terrain lies an enormous caldera formed during a catastrophic eruption approximately 640,000 years ago. Since then, Yellowstone has erupted on a smaller scale several times, with significant geothermal and seismic activity recorded throughout modern history. But this latest alert marks a serious shift in the situation. The red alert was issued after satellites detected unusual ground deformation patterns, an early and ominous sign of magma movement deep below the surface. Specifically, scientists observed uplift in a concentrated region within the caldera, suggesting that magma is pushing upward, displacing the crust above it. This isn't the first time such movements have been observed, but what sets this event apart is the rate, scope, and consistency of the deformation. Satellite-based INSAR interferometric synthetic aperture radar has shown that parts of the ground have risen several inches in just a few weeks, a pace that exceeds typical geothermal changes seen in Yellowstone. Geologists analyzing the satellite data cross-referenced it with ground-based seismographs and GPS stations scattered throughout the park. These instruments confirmed a surge in microseismic activity, small, often imperceptible earthquakes that occur when rock fractures under pressure. Such quakes are often a sign that magma is forcing its way into new cracks in the crust. While Yellowstone regularly experiences thousands of these tiny quakes each year, the sheer clustering and depth of these recent tremors align unnervingly with the satellite observations. The pattern suggests that magma is not only moving but doing so at an accelerating rate. What makes this development especially significant is that Yellowstone operates very differently from typical volcanoes. Rather than a single cone-shaped peak, the Yellowstone Supervolcano is a vast underground reservoir of molten rock that spans an area of roughly 30 by 45 miles. When pressure builds, the crust can eventually fracture in a catastrophic release of energy, potentially launching vast quantities of ash and gas into the atmosphere. This would not only devastate the immediate region but could also affect global climate patterns, agriculture, and economies worldwide. As scientists delved deeper into the implications of the satellite findings, they identified anomalies in gas emissions from several of the park's geothermal features. A measurable increase in carbon dioxide and sulfur dioxide, both telltale signs of rising magma, has been recorded. These gases typically leak from magma as it ascends closer to the surface, driven by the immense heat and pressure below. The concentrations of these emissions are now higher than what has been seen in decades, providing further evidence that the system is becoming more active. Thermal imaging has also revealed expanding hotspots across the park. Infrared satellite data shows elevated surface temperatures in new regions, far beyond the usual geothermal zones. This kind of widespread thermal shift could indicate the presence of fresh magma pockets closer to the surface than previously thought. While these signs do not confirm an imminent eruption, they do represent a marked escalation in volcanic unrest, compelling enough to justify the rare red alert status. The issuance of a red alert by geological authorities is not done lightly. It represents the highest level of concern and is typically reserved for situations where volcanic activity is escalating in ways that pose potential hazards to both the local environment and the broader region. In Yellowstone's case, the implications of such an alert extend well beyond the boundaries of the national park. A super eruption, while not guaranteed, is a worst-case scenario that scientists must prepare for with vigilance. And while this recent activity does not confirm that such an event is near, it has forced scientists to reevaluate their models and predictions. Understanding Yellowstone's behavior is notoriously difficult due to its immense complexity. The magma chamber beneath the park consists of multiple layers of partially molten rock, and its behavior can change rapidly. Small surges of magma may cool without incident, or they may initiate a chain reaction of rising pressure and fracturing rock. The satellite data revealing rapid deformation suggests that a significant pulse of magma may have entered the system, an event that can either stabilize as the magma cools or push the system closer to a critical threshold. Beyond the geological indicators, the red alert has serious practical implications. It activates emergency protocols for agencies monitoring Yellowstone, including increased aerial surveillance, enhanced thermal imaging sweeps, and coordinated data sharing between academic and governmental institutions. Moreover, the alert compels nearby communities to review evacuation procedures, update communication systems, and prepare for a range of potential hazards from ashfall to ground instability. The scale of potential impact, should the supervolcano erupt, is almost beyond comprehension. An eruption of Yellowstone's full magnitude could bury much of North America under a thick layer of volcanic ash. Crops could fail due to lack of sunlight and contaminated soil, while air travel would be paralyzed globally due to the ash cloud. Entire ecosystems would be disrupted, and climate patterns could shift dramatically as sulfur particles high in the atmosphere reflect sunlight and lower global temperatures. Though such an outcome remains unlikely in the immediate future, the red alert signals a growing probability that the system is entering a more volatile phase. Adding to the concern is the historical pattern of eruptions. Yellowstone has experienced 3 super eruptions in the past 2.1 million years. These occurred approximately 640,000, 1.3 million, and 2.1 million years ago. While this does not establish a rigid timeline for future eruptions, it highlights the cyclical nature of the volcanic activity. The latest data suggest that we are not just seeing routine fluctuations, but something more akin to the early stages of system-wide reactivation. Satellite detection of subsurface changes offers a unique advantage: the ability to monitor vast and remote regions in near real time. These satellites can detect even minute changes in ground elevation, temperature, and gas emissions. In the case of Yellowstone, the role of space-based monitoring has become indispensable. Without it, the scale and scope of the recent deformation might have gone unnoticed for weeks or even months. By catching these early signs, scientists have a better chance to model potential outcomes and guide public safety responses accordingly. Yet, even with all this technology, Yellowstone remains largely unpredictable. Magma movement doesn't always lead to an eruption. In many cases, it can stall or reverse course. However, the intensity of current signals, the rapid ground deformation, elevated seismic activity, increasing gas emissions, and thermal anomalies marks a turning point in how geologists perceive the threat level. It's not simply a matter of if, but of how far the system is moving toward instability. One particularly concerning development is the detection of harmonic tremors in the region. These low-frequency earthquakes are often associated with the movement of magma, and they differ from typical tectonic quakes in that they tend to persist and resonate like the vibrations of a tuning fork. The presence of harmonic tremors suggests that magma is flowing in a sustained manner, which can signal the approach of a more active phase. Though not always a prelude to eruption, their occurrence during this period of uplift adds another layer of urgency to the situation. Scientists are also exploring how interconnected the different chambers beneath Yellowstone truly are. Some data suggest that the upper and lower magma reservoirs, previously thought to be mostly separate, may actually interact more dynamically than assumed. If pressure builds in one chamber and transfers to another, it could accelerate changes across the system. The satellite imagery, when combined with deep seismic tomography, offers clues that pressure redistribution is happening now, perhaps for the first time in centuries on this scale. From a global perspective, Yellowstone is one of only a handful of supervolcanoes identified on Earth. Others include Toba in Indonesia, Taupo in New Zealand, and Campi Flegrei in Italy. Each has the capacity to trigger climate-altering eruptions, but few are as closely monitored as Yellowstone due to its location in a heavily populated continent and its history of explosive activity. The red alert issued here is not just an American concern, it is a planetary one. The detection of significant geothermal shifts by satellites has prompted the scientific community to intensify its focus on Yellowstone. Research teams from across the globe are contributing data and insights, hoping to build a clearer picture of what is unfolding beneath the surface. Field teams are drilling new boreholes to sample subsurface gases and temperatures. Advanced simulations are being run in laboratories to model potential eruption scenarios under current conditions. The red alert has, in essence, galvanized the global scientific community into action. Despite the rising tension, it is important to understand that a red alert does not forecast a guaranteed disaster. Instead, it marks a phase of critical observation, requiring constant monitoring and re-evaluation. Geologists are acutely aware of the need for precision, given the potential consequences of both underreacting and overreacting. But as data continues to stream in from satellites, sensors, and ground stations, the consensus is clear. Yellowstone is not dormant, it is stirring. This stirring carries with it a weight of uncertainty that presses on the minds of experts and citizens alike. The supervolcano has always held a latent power beneath its rugged beauty, but now that power is once again edging toward the surface. While time will ultimately reveal the path this awakening will take, one thing is certain: the eyes of the world are now fixed on Yellowstone, and every tremor, every uplift, and every satellite ping is being watched with bated breath. Beneath the surface of Yellowstone, changes are unfolding at a scale and speed not previously recorded in recent geological history. With the red alert now active, researchers are shifting from passive observation to a phase of urgent investigation. The satellite findings, while alarming in themselves, have triggered a cascade of focused studies aimed at deciphering exactly what is occurring within the supervolcano's vast underground structure. This is not a situation of speculation or exaggeration, it's a tangible shift in a complex and powerful natural system whose behavior could have unprecedented consequences. One of the primary concerns emerging from the current data is the behavior of the hydrothermal systems that dot Yellowstone's landscape. These features, which include geysers, hot springs, fumaroles, and mud pots, act as surface expressions of the activity happening far below. Over the last few weeks, notable changes have been observed in several of these geothermal sites. Eruption intervals for geysers like Steamboat and Giant have shortened significantly, and some smaller geysers that were dormant for years have suddenly sprung to life. In parallel, geologists have recorded abnormal temperature surges in hot springs, which could indicate heat transfer from rising magma below the water table. Hydrological models are now being recalibrated to understand the influence of heat and gas influx on the region's subterranean water reservoirs. As magma rises, it heats underground water, increasing the pressure within the porous rock systems. This can create volatile conditions in which sudden steam explosions, phreatic eruptions, may occur without warning. While these explosions are localized compared to a full volcanic eruption, they are capable of launching rocks and debris hundreds of meters into the air. Several of these mini eruptions have already been reported in remote areas of the park, scattering hydrothermal deposits and altering the terrain. These incidents, once rare, are becoming more frequent, a worrying trend for researchers tracking volcanic evolution. Beyond these surface expressions, a more subtle but no less vital sign of change is being observed in Yellowstone's magnetic and gravitational fields. Satellite magnetometers and gravimeters are registering shifts in both parameters, phenomena that suggest large-scale movement of molten rock. Changes in magnetic field intensity can result from heat altering the alignment of magnetic minerals in the crust. Similarly, variations in gravity can occur when magma accumulates in previously empty chambers, increasing the local mass. These physical indicators, though invisible to the naked eye, are among the most sensitive tools geophysicists have for interpreting deep Earth processes. Their sudden fluctuation is not taken lightly. The geopolitical relevance of Yellowstone's activity cannot be ignored either. Government agencies, including FEMA, the USGS, and the Department of the Interior, have activated interagency coordination centers. The Department of Defense has reportedly reviewed emergency response scenarios, not just for public safety within the region, but for safeguarding critical infrastructure across the continental United States. Yellowstone's proximity to major agricultural zones, freshwater sources, and transportation networks adds a layer of strategic risk that elevates its threat from a geological concern to a matter of national preparedness. On the international front, allied scientific agencies are also weighing in. Satellite constellations from Europe, Japan, and Canada have been tasked with additional observation of the region. The global scientific community recognizes that Yellowstone's potential impact is not confined to North America. If a super eruption were to occur, it would inject massive amounts of ash and aerosols into the stratosphere, reducing global sunlight and triggering what is known as a volcanic winter. This kind of event could reduce average global temperatures by several degrees for years, disrupting ecosystems, agriculture, and even geopolitical stability. Crops could fail in regions thousands of miles away due to shortened growing seasons and altered weather patterns. Within the realm of ecological science, biologists and conservationists are closely watching Yellowstone's wildlife, which may serve as early indicators of further volcanic disturbances. Several species in the park, especially those sensitive to ground vibrations and atmospheric changes, have exhibited unusual behavior. Herds of bison and elk have been migrating erratically, moving away from traditionally safe grazing areas and congregating at atypical altitudes. Birds known for nesting near geothermal areas are now being spotted farther afield. While no single behavioral anomaly is definitive, the collective pattern points to a subtle environmental awareness animals possess, an awareness that in many cases precedes seismic events. Parallel to wildlife shifts, there has been a sharp spike in mineral content in surface waters. Streams, rivers, and lakes within Yellowstone's ecosystem are showing elevated levels of elements like arsenic, lead, and mercury. These toxins are typically trapped in the rock below, but can be released when geothermal fluids rise through fractures. The change is already impacting the aquatic food chain and poses a serious risk to downstream water users. This adds an environmental hazard to the already complicated picture of geological unrest. Another dimension of this evolving crisis is the role of the public in interpreting and reacting to the news. With the red alert now public knowledge, park visitation patterns have begun to shift. While some tourists are drawn by curiosity or thrill-seeking behavior, others are avoiding the region entirely. Local businesses, which depend on seasonal tourism, are facing deep uncertainty. Emergency communication strategies are being revised in real time to ensure clear, accurate updates reach residents and visitors. The challenge lies in conveying the seriousness of the threat without inciting panic, while also ensuring that preparedness steps are actually taken. Amidst this, schools and universities in surrounding states are beginning to incorporate real-time geological data into their science curricula, turning a potential catastrophe into an extraordinary learning opportunity. Students are using live GPS data, satellite imagery, and seismic readings to engage with one of Earth's most powerful natural phenomena. Educational institutions are also working with emergency services to design youth-focused safety plans, recognizing that community-wide preparedness begins with awareness at all levels. In terms of modeling future outcomes, advances in artificial intelligence and machine learning are now playing a critical role. Volcanologists are feeding thousands of data points, from historical eruption sequences to live seismic, gas, and temperature data, into predictive models, trained to detect complex patterns and predict potential eruption scenarios with increasing precision. The use of AI has revealed previously unnoticed correlations between various geological indicators. Some models suggest that if current patterns continue without stabilization, the window for a moderate-scale eruption, not a super eruption, but a significant event, could shrink to mere months. Others indicate a chance for temporary stabilization if magma cools or finds lateral escape pathways instead of forcing a vertical ascent. The engineering community is also contributing, focusing on infrastructure resilience. Structural assessments are being conducted for buildings, bridges, and power stations within a 500-mile radius of Yellowstone. Engineers are analyzing ash load capacities, water contamination risks, and seismic resistance. Municipal water supplies are being tested and reinforced. Hospitals are updating filtration systems to handle possible air quality deterioration from ash. The entire region is essentially preparing for an event that may not come, but the cost of not preparing is simply too high to ignore. Crucially, the red alert has rekindled philosophical and ethical debates about humanity's place within Earth's broader systems. Yellowstone is a stark reminder of forces that predate humanity and will likely outlast it. The supervolcano's emergence in scientific discourse over the past century has often been cloaked in language of awe, fear, and helplessness. But today's response is different. It is scientific, coordinated, and proactive. Instead of passively awaiting fate, experts from dozens of disciplines are working in unison, applying the best tools of the modern world to understand and, if possible, mitigate the worst nature can offer. And if you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Yellowstone's sudden shift, natural cycle, or eruption warning? We want to hear from you. Thank you for watching and see you next time.